So I'll be talking about derandomization. More specifically, I'll be talking about one problem, which is undirected ST connectivity, and I'll be presenting a derandomized algorithm for this. So the problem is simple. So you are given a graph and you are given two nodes S and T, and what you need to check is whether S and T are connected. So if we want to talk formally, if we want to define the language formally, we could define it as the set of all encodings of GST such that there exists paths from S to T. So that's simple enough. And we'll only be seeing undirected graphs here. For it becomes a bit more complicated in the directed graph case. So yeah. So let's say, so first of all, so we want to look at algorithms which, so we want to look at the space complexity of such algorithms. So let's say I first want to give you a, so to show derandomized, to show the derandomized algorithm, I'll first need to show a randomized algorithm which we will then derandomize. So the algorithm which we consider is, so let's say you are at S and you want to check whether you can reach from S to T. So what would be the simplest method would be to do a sort of random walk on S. So random walk on the graph. So what you do is you start from S, pick a random edge, travel along it and reach over here. Then you take any other edge connecting this and then you keep traveling along that. And eventually, so if you reach T, then what you do is you output true that S and T are connected. And if you don't ever reach T, then you say that it's not connected. So yeah, that's the simple algo. So what you do is you do random walk starting from S, and output 1 if we reach T, else 0. So yeah, so that's a simple algorithm. Now we need to check, so we need to see how many, so how long our random walk should be to make sure that we, so with some high probability we are able to detect it. So first of all, to note that if S and T are not connected, so if GST is not in, so if they are not connected, then you can say that this does not belong to USTCon, and so we know that, and our algorithm will always output 0, because since you can't reach from S to T, then our algorithm always outputs 0 because you won't be able to reach from a random walk. So the in this case the probability that our algo is correct is 1. So we can do it in, so we can do it with 1 probability, it will always output 0, which is the correct answer. The next problem is a bit more interesting. So you are at GS, so you know that there is a path from S to T, and you want to estimate how long your path should be. So then first thing to note is that so I'm going to present a sort of theorem which will not prove here because it would take quite a long time, but the general idea of the proof is that the general idea of the theorem is that, let's say X is the random variable, so X is the random variable representing the number of steps the random walk takes to get to T. So it represents the number of steps taken to reach T. Then we know that then there's a theorem which states that the expectation of X, so the expected value of X, so this is called the hitting time, and in fact the expected value of X is called the hitting time, and we know that this thing is less than equal to 2 times mod of E. This is a standard theorem which you can find in many books. The proof is a bit difficult, so we'll not get into that right now. So the expectation of x, the expected number of steps you will need to take to get to reach t would be less than equal to 2 times size of e. So now let's say, so what we say is that we do a random walk starting from s of length, let's say 4 times mod e. In this case, what will we have? So the probability that our algorithm outputs correct will be equal to the probability that the random variable x that we have was less than, let's say, so yeah, it would be less equal to probability that x is less than, let's say, mod e. Yeah, no, sorry, it would be 4 times mod e, because if we can reach this, if we can reach from s to t in 4 times mod e steps, in less than equal to 4 times mod e steps, then our algorithm outputs true, because it's correct, because we were able to reach from s to t in 4 times mod e steps. So this can also be written as 1 minus probability that x is greater than 4 times mod e. Now we use Markov's inequality. So by Markov's inequality, we can use Markov's inequality because x only takes positive values by the way that we have defined it. So we use Markov's inequality, and we have that this thing will be less than equal to expectation of x by 4 times mod e. And expectation of x, the mean of x is given by, so the mean of x will be given by, as we saw, it would be less than equal to, so it will be less than equal to 2 times mod e, and so you have this. So we see that the probability that x is greater than 4 times mod e is less than equal to half, which means that the probability that x is less than equal to 4 times mod e is greater than equal to half. So which means that our algorithm outputs correct. Our algorithm gives the correct output with greater than equal to half probability. So this shows that this is a valid. So this is a valid algorithm. It's a valid algorithm in RL. Okay. So now we need to analyze its space complexity, how much space it takes. So note that all you need to maintain is the current node that you are at. So that can be done. So let's say you have n nodes, n vertices. Then we can, so all you need to store is a number corresponding to n. So all you need to store is log n. All you need to store is log n. So it would be like order log n. And also, I mean, so we are taking 4 times mod e of steps. I guess that's not important, but so the size of e will be equal to, so it would be order n square. So the algorithm is actually also polynomial in running time. So that's good. But this algorithm gives the correct output with probability. So if the input is correct, then it outputs with probability greater than half correct, and if the input is not in the set, then it outputs with probability 1 correct answer. So this shows that the algorithm that we just provided shows that the problem of detecting ST connectivity in undirected graphs is in RL. So that's good. But now comes the idea of derandomization. So the idea of derandomizing such a algorithm is, so you can see what we are doing right now is we are going along. So you are starting at S and we are going along some random paths from this. But the idea of derandomization is you start from S and you go along every possible path and you check for every possible path whether whether you can go from S to T or not. So you check all paths emerging from S, and if in any of the paths you see T, then you output 1, otherwise you output false. The main thing to note would be that in this case, so how many paths would you have to store? So you could enumerate, so all you need to do is you need to enumerate all the paths. And so let's say your graph is like D regular. Just for an example, let's say your graph was D regular. Then how many paths would you have? The number of paths you would have would be of order D power n. So you would need to enumerate all of those, and enumerating all of them would take logarithm times complexity. So finally the time taken would be n log d, which is, this would not be the time, this would be the space actually. So yeah, the space complexity Sn would be order log dn, log of d raised to the power n, which is order n. So this is not logarithmic in n, it's polynomial in input size, which is not good. So yeah, that's the idea. But now let's consider a very special class of graphs. So let's say we consider graphs such that the diameter of the graph, which is the longest path that you can consider. So consider those graphs which have diameter of length logarithmic. So these are, so we are considering such a class of graphs. And then what can we say about the complexity of this thing? So again, you need to enumerate all the paths, but you would only need to check for paths of length log n, because so you know that the longest path that you can get has size log n. So this has size log n, and every other path that you can possibly construct has size less than log n. So all you need to do is check for paths of length log n, and then you'd be done. If you find a path of length, if you find t in any of the paths, then you know that the answer is true. Otherwise, you know that the answer is false, because you have checked all the graphs, all the paths. So in such a case, what would be the time complexity? So we know that the diameter is order log n, and we are only checking paths of length log n. So let's say the graph again was d regular, let's say the maximum degree was d. Then we know that the number of paths is less than equal to d times some order log n. And so to enumerate all the paths, so you'd only need to enumerate, and then you could traverse through all of them. So to illuminate the paths, what you'll need, the space that you'll need would be log of this thing. So this is, so this can be done in like order log n into log d. And if you assume d to be a constant, we'll see how we can work that out later, but if we assume d to be the constant, this is order log n. So yeah, we have found, so for graphs with the diameter of log n, log of the input size, log of the number of vertices, we have found we have derandomized the algo, and we have found actually a LogSpace algorithm for ST connectivity, undirected ST connectivity. The next idea would be to show how we can do this for general graphs. So the idea is to, given a general graph G, what you would like to do is you would like to transform G. So let's say you are given some graph G. What you would like to do is you would like to transform G into another graph, let's say H, such that if S and T were connected in this graph, then they would also be connected in this graph. So what you'd have is that the connectivity property remains conserved. So if ST are connected in here, ST should also be connected over here. And what you want is that the graph H should have logarithmic size, logarithmic diameter. And if you could do that, then if you could do this using only logarithmic space, then you would have then we know that we can solve, then we can check whether this graph, whether S and T are connected in this graph, and then we know that they'd be connected in the original graphs. So this is the idea, and to introduce this concept we need to introduce a few more concepts, the first of which is expander graphs. So expander graphs, so there's multiple definitions for this, but we'll be working with two specifically. So intuitively speaking, a graph is an expander graph if it satisfies two properties. So G is, so I'll get to the formal definition later. Let's consider a general definition now. So so we say that a graph is an expander if it satisfies two properties. The first is that it's sparse, and the second property is that it's well connected. So what do we mean by sparseness and well connected? So sparseness is intuitive, so it means that you don't have that many edges. So what this means is that you do, so each of the vertices does not have too many each of the vertices does not have too many edges coming out of it. So that's the idea of sparseness. And well connected means that you can get from one node to the other without taking many steps. So the idea is, if you are over here and you want to go to any other graph, you want to go to any other node, and you can do it in small number of you can do it in less number of steps. So you can see how these two things are contrasting. So you can say that if the graph, so let's consider for example a complete graph on n vertices. So we know that this is fully connected, and it's not sparse because it's entirely dense. In fact, it's the most dense graph possible, and it's also obviously well connected. It's the least sparse graph actually. I think I made some mistake. So Kn, the complete graph on n vertices, it's the least sparse graph because because of the fact that obviously we have every possible edge in it, but it's very highly well connected because you can go from any node to any node in just one step. On the other hand, let's consider something like a empty graph would be trivial, but yeah, that would be the most trivial case. That would be one end of the spectrum in which you have no connections, so it's entirely sparse but it's not well connected. So you can see most graph would lie in somewhere in between. But we want to consider expander graphs which are both sparse and well connected. And yeah, so that's the general intuition for expander graphs, and you can see why we need well connectedness. So the idea of well connectedness means that you can get from one path to the other in a small number of steps, and we actually show that under some formal definition of expander graphs that this length comes out to be logarithmic, which we showed earlier was useful for our purposes of solving undirected ST connectivity. So now we have the formal definition. So sparse, so we say that a graph G is a let's say Ka expander if we have two properties. First property is that the graph is sparse, and by sparseness we give a formal definition, that is there exists an integer d. So basically the graph is d-regular, so we want that the graph G is d-regular, and we generally want that d should be a small number. So in fact we define families of expander graphs, and we want that in the families of expander graphs that d has constant size. So yeah, that's what we mean by sparseness, that it has so it's d-regular and where d is some small thing. And next we want well connectedness, and this is formally defined by, so we say that a graph is well connected for our purposes is if for any subset S of size V. such that size of S is less than equal to k. If S prime equal to V minus S, which means all sets, so it's basically S complement. So if S prime is S complement, then number of edges from S to S prime is greater than equal to A times mod S. So you can imagine it. So you given a graph. So let's say we have a graph, and the expander means, so the second property, well connectedness, means that given any subset of the nodes. So yeah, given any subset of the nodes, the number of edges going out from this thing is greater than equal to A times mod S, and this number of edges going out means that the size of the neighborhood set is greater than equal to A times mod S. So yeah, there's that. And this is the definition. And so one thing immediately follows from this definition, which we shall prove. And this thing is that so this is like a, let's say, a theorem that if G is a Ka expander then for some large K, so if K, so yeah, let's write it like this, then if K is equal to order n, we have the following. We have or let's just write it as, then G has a logarithmic diameter. We'll just write it like this. So the proof is also not very difficult actually, so let's just do it. So let's say you are given a, so yeah, let's say you are given a K expander and you want to find its diameter. So what would you do? So let's say the diameter starts from S and ends at some node T. So what would you do? So consider first S1, the set S1, which you define as only the set containing S. Then note that S1, then we use the property of the expander graph, the second property of it being well connected, to define S2 to be the set of all vertices such that there exists edge from S1, there exists edge from S1 to B. Then using property of expanders, we have size of S2 should be greater than equal to A into size of S1, which is just 1. Similarly, we define S3 as the set of all vertices V such that there exists edge from S2 to V. So notice what this means. So this equivalently, this can be written as the set of all vertices V such that there exists path of length V, path of length 3, or rather path of length 2, from whereby length I mean number of edges. So there exists path of length 2 from S to V. And similarly, this would be the set of all vertices such that there exists a path of length 1 from S to V. So yeah, so we'd have this, and again using expander property, and we can use that because we know that K is order n. We know that this one has size greater than equal to A into size of S2, which is A again, which is greater than equal to K. So you have this thing, and similarly you can keep doing this and you get ST, which would be the set of all vertices V such that, so basically distance between S and V is less than T, less than, let's say, T, yeah, T minus 1, or let's say, yeah, T minus 1, or let's say, let's call it something else, otherwise we'll confuse it. Let's call it SM. Oh sorry, So yeah, we'll have this, and we know that size of Sm would be greater than equal to a power m. In fact, m minus 1 again. So now let's say, so we know that we can keep doing this until we reach t. Once we reach t, we find then so yeah, if we reach t, let's say this distance was the diameter was some length, let's say d, then we know that in st, so we know that t would lie in sd. And when this would occur, and when this happens, we would know that we have considered all the paths of length. So yeah, we would know that we had traversed all paths of length d, and so we basically sd would be equal to the entire vertex set, because we had traveled all the vertices. Assume currently we are currently assuming that the graph is connected to define these k expanders, etc., etc., at least for this one. So yeah, I think I should write that if G is connected, I mean, if it's not connected, then you can just work on the connected component in which you have the largest diameter, and you'd get the same thing. So let's say SD equal to V in the case of a connected graph, and we get, more specifically, we get size of D, which is equal to N, which from this fact, and we know that again we saw that the size of SD would be greater than equal to a power D minus D, let's say, yeah. In fact, here all of these should be plus 1, and so this means that D is order log n. So you see that the diameter is actually logarithmic in the number of vertices, which is a good property to have, as we saw earlier. So we showed that the diameter of an expander graph is always logarithmic. So we know that the so we know we can solve ST connectivity for an expander graph in logarithmic time deterministically using our derandomized algorithm. So yeah, let's continue. So this was one way to define. So yeah, this was one way to define expander graphs. There's also an equivalent measure of well connectedness. So let's just let it as equivalent measure of well connectedness. So currently we were using the concept of an expansion. So we were saying that if you have a subset S, then it expands to its neighborhood set expands. So equivalent measure of well connectedness. Now we'll look at a sort of algebraic definition of well connectedness. So consider a graph G which is sparse, which means it's deregular, and for now let's say it's connected and non-bipartite. This is just a technical thing that we'll not need actually, but let's just mention it. So if all this holds true, then we can define the adjacency matrix. So of course we can divide it for anything, but we can define M as 1 by D times A, where A is the adjacency matrix. In such a case, we have, so yeah, this is, so now if you look so yeah, so if we are trying to measure well connectedness, so another measure of well connectedness would be to see how fast the random walk on this converges. So yeah, let's say you start from S and you have the entire graph. So you have the graph with many vertices, and you start from S, you choose any random vertex, you choose any random edge, move along that and keep repeating this. So what you'd have is a probability distribution over all the vertices, and as time goes on, if you keep taking these steps, you'd notice that this thing converges to this would converge to a steady state distribution. So what you'd have at the final end would be, so you'll have 1 everywhere and 1 by d over here. So the probability of finding yourself in any of the vertices would be constant, so it would all be the same. And so for well connected graphs, you can imagine, for well connected graphs, since there would be many connections between vertices, this would happen very rapidly. So you can imagine, let's say you have, so this is well connected, means you can go from here to here in less time, and so the probability spreads very rapidly and it converges very rapidly as well. So yeah, that's how it works. So yeah, so we want to measure, so well connectedness is connected to the how fast this thing converges, the random walk converges, and we'll see now that the random walk, the connection of the random walk, the rate at which the random walk converges can be associated to a specific eigenvalue of this matrix, in fact the second largest eigenvalue of this matrix. So let's just see. So if you have m equal to 1 by d times a, and let's say you have some probability distribution vector p. So what p is that p is a probability distribution over the set of vertices. So this means that summation over all vertices v, pv is equal to 1, and all pv's are in like 0 to 1 inclusive. Let's say, so now let's say you know that you are in such a probability distribution, and you take one random step from wherever you were, then what would be the new probability distribution over state? So the main thing to note is that so the probability of, so let's say this was pt, and you at the tth iteration, and you move from pt to pt plus 1. So how do you calculate pt plus 1 given you know pt? So you use the simple probability theorem, and you will get, so the probability of finding you at, let's say, the vth vertex at step t plus 1 would be equal to the probability that you were at v at the tth step, or let's write it in a better way. So it would be equal to the set of all, so you sum over all the edges. So let's say you want to find the probability of being at v, and you can come into v from a bunch of vertices. So you sum over all such edges, and what you do is you add the probability that you were at v at the tth step, and that you actually choose this path, and like a transition probability. And what this transition probability is that it's 1 by d, because if you were at this u over here, in fact this was a u, sorry. So if you were at u over here, and and it had d edges, so you would choose this with 1 by d probability. So this can in fact be written as equal, so yeah, this is something, and you can in fact write it as m times p t. But in fact, let's write it in a better way. So in fact you could write pt plus 1 is equal to m times pt. Why is that? Because you need to observe that the summation over uv in E of 1 by d times pt of u will be equal to, so it will be equal to summation over all the u's into muv times, or rather mvu, because it's symmetric, so it actually doesn't matter, into pt of u. And this you will find is like the definition of matrix multiplication. So yeah, you have this thing. So in fact, if you keep applying this, you will get pt plus 1, or rather just pt to be equal to m raised to the power t times p0, where p0 was your some initial probability distribution. It could just be like 1 somewhere and 0 elsewhere. So yeah, this is good. PT is good. And now you want to see how fast PT converges to, let's say, pi, where pi is your stationary distribution. So what would be the stationary distribution? It would be 1 by mod v times once. So yeah, that's the PT. So what you'd need is you'd estimate. So to estimate this, you'd first let's make a few observations which will help us. So consider m pi. What would be m pi? If you actually do the product, you will find that it would just be equal to pi itself, because so any row of m would be would have 1 by d at d places and 0 everywhere else. And when you multiply it by the 1 vectors, what you'd get is 1 by d plus 1 by d times, and when you add that, it just becomes 1. So you'd be left with the same thing. So in fact, m pi equal to pi. This means that pi is an eigenvector with eigenvalue 1. So yeah, that's something. And another thing to note is that all the eigenvalues of m, so all eigenvalues of m are less than equal to 1. How do we know this? You can see this from the fact that, so let's assume mv equal to lambda v. So lambda is an eigenvalue of m. Then you'll have to note that the row of one row of m, when multiplied it with a column vector like v, what you are doing is you are essentially taking d of these and you are taking their average. So yeah, my matrix multiplication would be like taking average of a few of these things. And when you are taking average, you know that the magnitude can't increase. So any of these would be averages of a few of the elements of V. So you know that when you are taking average of a bunch of elements, it can't exceed the maximum value of the others. So what you have is, so if there was a lambda over here, it must be less than 1. Yeah, so that's the theorem. So this means that lambda is less than or equal to 1. So yeah, we know all of this stuff. Very good. Let's continue. We wanted to estimate how fast PT converges to pi. So we want to estimate this difference, PT minus pi by P naught minus pi. Why we want P naught minus pi is because we would like to calculate the relative error. So our rate of convergence should not depend on our starting point. So anyways, so one thing to note would be that you could write the numerator as m raised to the power t times P naught minus m raised to the power t times pi. Which would be this thing. Now we use another observation. P naught minus pi is perpendicular to pi. How do we know that? Because consider P naught minus pi dot product with pi. Let's say you are doing the dot product. What you get is P naught dot product with pi minus pi dot product with pi. Now P naught is a probability distribution. Let's say you have some probability distribution and you multiply it with a vector of all ones. What will you be left with? And there's also like a constant over here. So when you add all of these up, what you get is just 1. Similarly, pi is also another probability distribution, and so pi is like 1 by mod v times, so it has all the elements are 1 by mod v, 1 by mod v, 1 by mod v. So in fact when you add you'll get you'll be left with 1 again. So in fact these both are equal and their difference will be 0. So yeah, what we have is this observation that p naught minus pi is perpendicular to pi, and we saw that pi was pi was an eigenvector, and in fact it was the largest eigenvector because all the eigenvalues were less than equal to 1. So we use the familiar theorem of linear algebra, which states that the maximum over all x such that x is perpendicular to v1 of norm of ax by norm of x is equal to lambda 2, where, so let me just write it, where v1 is largest eigenvector. So what largest eigenvector means, means the eigenvector corresponding to the largest eigenvalue. So where v1 is the largest eigenvector and lambda 2 is the second largest eigenvector. Second largest eigenvalue in fact. Lambda 2 is a eigenvalue, yeah. So now we can use this in our above statement, and we find that this can be written as, so since we know that p naught minus pi is perpendicular to pi, we see that this can be written as, so it would be less than equal to the maximum. So the maximum is lambda 2 and this lambda 2 of a. So yeah, when I talk about eigenvalues and eigenvectors, I'm talking about a over here of a. So here we'll have less than equal to lambda 2 of m power t, and we know that lambda 2 of m power t is lambda 2 of m raised to the power t. So we in fact found a very nice convergence thing. So we saw that the convergence of the random walk, how fast pt tends to pi, depends on the second largest eigenvalue, which is a very interesting fact. Yeah. So yeah, that's very good. So in fact the second largest eigenvalue is a very important thing, at least when we are talking about the convergence of random walks and all that. So now let us consider, so yeah, then we define something called spectral expansion. We say that if so we define the spectral expansion of a graph G as 1 minus lambda 2 times G, where lambda 2 of G means the second largest eigenvalue of the adjacency matrix. And yeah, so we see that if the graph is well connected, lambda G will be large, because if lambda G is large, then lambda 2 is small, which means that our random walk converges rapidly. So this is called the mixing time, I think. So yeah, the mixing time of the Markov chain will be small. So yeah, that's the thing. And then we have a theorem which I shall not discuss, but it's a very interesting theorem because it relates the notion of the spectral expansion that we did to the original notion of expander graphs that we so the original way of this we defined. So the theorem basically says that if the graph has spectral expansion, so if it's a spectral expansion, then it also has vertex expansion and vice versa. So essentially both of them will be equivalent. So if you have large spectral expansion, then you have large vertex expansion, and similarly the opposite side. So yeah, this was a very interesting theorem. Yeah, this essentially proves that the way we defined it earlier, the way we defined expander graphs earlier, could also be defined using spectral expansion. So that's fine. Yeah, so now we have figured out a way to think about graphs and define, in fact, expander graphs, which we know have logarithm parameter. So now we build tools which we need later to convert graphs to these expander types of graphs. So what we do is we have so we define a few things first. So the idea is that we want, given a graph, we want to convert it, so we want to transform it to a graph G prime such that G prime is an expander graph and that the property of connectedness remains conserved. So yeah, we want to do this sort of construction. So how would we do that? So how would we go about doing that is so the idea is that we apply on G some, so what we do is we apply some operation which increases its sparseness, which decreases its sparseness but it increases its well connectedness to get a sort of intermediate graph, and then on the intermediate graph we apply some other transform which again increases the sparseness by quite a bit but brings down the well connectedness by only a small margin, such that the final graph that we have, GF, is better than G in terms of the sparseness and well connectedness. So this allows us to construct families of expander graphs. So the first of these things, so the first of such transforms is the squaring transform. So what do we mean by squaring a graph? So yeah, given a graph G, let's say it's V comma E. G square is the set. So G square is a graph with the same vertex set, but a new edge set, such that ij is in E prime if there exists a path of length 2, of length less than equal to 2 from I to j. So yeah, basically let's say you have some graphs. So yeah, let's say you have some graph and I want you to construct its expand, so I want to square the graph. So what I'll do is I'll join all the paths which are length 2. So I'll join this and I'll join this with this and I'll join this with this and I'll also join this with this, because there's also a path to length 2 path from here to get the new graph, which is nice. So first, so how many neighbors would each of the nodes have? So okay, let's say your original graph was, so let's say originally the graph is deregular. What can we say about the regularity, let's say, of the new graph of G square? Then note that, so let's say we know that this guy has D neighbors. So let's say we choose one of them and this guy again has D neighbors, and so we can choose anyone from them, and so we get D square. So this might lead to some overcounting. So let's say you have this case, so you are overcounting this, but in general you can say that the new graph G square will have order D square regularity, and in fact you can show that with some modifications of this you can show that G square it would be exactly in fact D square regular. So yeah, that's nice. That's how we define the squaring, but in fact it's not good, because so if it's D square regular, this means that you are decreasing the sparseness, because each of the nodes has more neighbors now. It has more edges coming out of it, and so the number of edges has gone up, which is not very good. So what you want is but one very good thing to note is that, so let's say lambda 2 of G square. What can we say about lambda 2 of G square? In fact, you can show that this will be equal to lambda 2 of g, the square of lambda 2 of g. So in fact, yeah, so you can see how, so lambda 2, since lambda 2 was less than 1, this thing is actually very small as compared to the original one. So yeah, you can see how, so yeah, basically the sparseness increases, but the well connectedness also increases. The sparseness decreases, but the well connectedness increases by a good margin. Yeah, that's how squaring works. The next problem would be, so yeah, now we need to make sure that our graph remains, so we need to bring down the regularity again. So the next transform that we use is something called the zigzag product, which is a bit more complicated than the squaring. So we denote it like this. So we say G1 Z G2. So the operands, when we want to do a zigzag product, the operands should satisfy some properties. So the first property is that G1, so G1 can be written as, let's say, V1 E1, where and it's D1 regular. So you assume that it's D1 regular, and you also assume that G2, which is V2 E2, is D2 regular, but you have a constraint that the size of V2 is equal to D1. So the number of, so the size of V2 is equal to the regularity of the first graph. And then you define G1 Z G2 as, so the vertex set is V1 cross V2, the cross product, the Cartesian product, and the new set, the edge set is E. So the edge set can be, so the describing the edge set requires a bit more work. So let's say your original graph was this of, so let's say this was G1. So when constructing the zigzag product, what you do is you replace each of these nodes with a replica of the bigger graph. And so yeah, then you will get V1 into V2 vertices, and then you create an edge from, so then you create edges in a sort of zigzag fashion. So you are over here, you take one small step within the cloud, then you take one large step across this cloud from here to here, and then from here to here, obeying a set of rules which I'll describe. And then you say that, so this describes one edge from here to here, so choose some different color here, and this is the, and yeah, after doing all this you'll get one edge, and you do this for all possible things. So to describe the, let's properly describe it. So let's say you have, this was U, so this was like the uth node of G1, and you had the corresponding this thing. So let's say you are given U comma I, and you say there exists an edge from U to UI to Vj. So basically, let's write it in a better way. So U comma I and V comma J is in E, which means that there exists an edge between these two, where I use the notation that, so by U comma I by, so yeah, this means that so yeah, u comma I and v comma j, between them there exists an edge. When you can do the following sort of transforms. So let's say you are at u comma I, where u means like the uth node in gi, the big node. We call these clouds. So these green things are called clouds. So the uth cloud, and within that the ith node. So you say that so you say that the transform works like this. So you are at u comma I, let's say, then you go to u comma I prime, where I prime, or yeah, if the following set of sort of these things exist. So you say that I prime is the bth neighbor of I. So this is like the notation. So I of b, which means the bth neighbor of I, is equal to I prime. And then note that I prime lies between d, so it lies between d1 minus 1 and 0. So in fact you can use it as the to identify the edge along which you want to travel. So u of I prime is equal to v. So basically this big node, so you choose the I primeth edge of u in the big graph between clouds, and you move along that, and then you say that, and then you choose a j prime such that v of j prime is equal to u. So you choose that vertex of v corresponding which you can, the jth primeth vertex of the j primeth neighbor is u, and then you choose a j such that j of a is equal to j prime, where a and b are like parameters. So yeah, they run like d2 cross d2. So yeah, this is like how you define it. So yeah, this is a very weird sort of transform. So basically it works in a similar way, in this way. So one thing to notice that so another way to describe it is that the abth neighbor, so the abth neighbor of u comma I is obtained as follows. Here a comma b belongs to d2 cross d2. So yeah, the abth neighbor of ui is obtained as follows. So what you do is you go from ib to, so let's write it in a better way. So you are at u comma I, and you go to u comma I prime such that I of b is equal to I prime. The bth neighbor of I is I prime, and after that you go to a vertex v. From here you go to a vertex v such that u of I prime equal to v. So basically you go to the I primeth neighbor of v, and you can do that because I prime lies between 0 to d minus 1. So you have this nice property, and after that you go to a j prime such that v of j prime is equal to u, and then you go from v comma j prime to v comma j in such a way that j of a is equal to j prime, where a was from the a comma b that we had taken earlier. So So yeah, you had this weird sort of this thing, and you can also note from this that if v comma j is the abth neighbor of u, if v comma j is the abth neighbor of u comma I, then v comma j will be the bath neighbor of v comma j. So yeah, this is a bit confusing, but yeah, that's how this zigzag product sort of thing. It's called the zigzag product because you sort of zigzag across the clouds. So you move once, then you travel across the clouds, then you move again. So yeah, that's how you describe the zigzag product, and this is how you construct this thing. Now you can, so first of all, to note that so each vertex u comma I has abth neighbors, and where ab range from d2 to d2. So what you have is, for each of these u comma I, you can choose a and b in d2 different ways. So each of these will be connected to d2 square vertices. So in fact, the degree of the graph, so g1 g1 zigzag product g2 is a d2 square regular graph, and there's also one theorem which again we shall not prove because again it will require quite a bit of working out, but you can see that so lambda 2 of this thing, the second eigenvalue of this, will be less than equal to it will be less than equal to lambda 2 of g1 plus lambda plus 2 times lambda 2 of g2. So that's one of the theorems. So you can see that the lambda 2 actually increases a bit, but the sparsity reduces by quite a lot, because note that g2 has size, so the size of g2 is equal to d1, where d1 is the regularity of the first graph. So what you can see is that d2 will be much smaller than d1 if you assume that g2 is sparse. And in fact, so this means that d2 square will also be much less than d1, or at the very least it will be less than d1. And so you can see that actually this thing goes down quite a lot. And in fact, you can use this to construct graphs, which, so you can construct a family of graph, the explicit construction I shall show in a while, for which the degree remains constant but the size keeps increasing. So yeah, that's the very useful thing. So yeah, this is how the zigzag product works. So you can see how it can help, right? So you can keep increasing the, so you saw that this thing became squared when we did the squaring. So the well connectedness increased. So if we do one bout of, let's say, squaring, then zigzag product. So if we first square, then we do a zigzag product, then the final graph that you would be left with would have a smaller, so it would be d2 square regular, so it would be, so the regularity would be small, but the well connectedness would have increased by quite a lot. So in fact, we can show this by an example. Let's consider one of the examples. So what we'll do in the example is we'll try to construct a explicit sort of graph. We'll give an explicit expansion of an expander graph family. So let's say H is a graph with, so let's say that it's a deregular graph. Let's say, so H is a deregular graph with d raised to the power 4 vertices, and let's say lambda 2 of G is less, lambda 2 of H, sorry, lambda 2 of H is less than equal to 1 by 8. So it's some good, so it's a fairly good, so it's a graph with a fairly good expansion, and also and it's also deregular with d power 4 vertices. So from this we can create a we'll create a family of graphs which have arbitrary size but are only d square regular and also have fairly good expansion. So how you do is that you define g1 to be equal to h square, and then you define each of gt gt is to be equal to gt minus 1 square tensor, not tensor, sorry, the zigzag product of this with h. Yeah, so you do this thing. So let's see how this, so let's see what the properties of these things would be. So my first claim is that, so claim 1, so my first claim would be that the size of gt is equal to d raised to the power 4t. So how do we prove this? So first of all, note that size of g1 is h square, which is d raised to the power 4, because the squaring does not change the number of vertices. So yeah, you have this thing, which is very nice. And then let's say how would you do it for g2? So we saw that the size of g2 will be equal to size of g1 square into size of h, because of what we saw earlier, that when you do the exact product, the sizes get multiplied. And we know that the size of g1 square is just the size of g1, which is d raised to the power 4. So this becomes d raised to the power 4 into d raised to the power 4, which is d raised to the power 8. And similarly, when you do g3, you'll be left with the size of g2 square, which will just be the size of g2, which is d power 8 into d power 4, this is d power 12. So yeah, inductively you can see that this all works out, and finally we'll have this thing. So yeah, that's good. And then we have the second claim. So this means that the size of the family of graph increases exponentially as we keep increasing t. So that's good. And my second claim is that gt is d square regular. So yeah, so again, so g1 will be, so g1 was defined as h square, and we know that squaring a graph increases its regularity, and since h was d regular, this is d square regular. So okay, how do I write? So g1 is d square regular. Now let's say we have g2. So now we are always doing zigzag product with h for all gt. We are always doing zigzag product with h, and we saw that the degree of the new graph that is formed is equal to the squared regularity of this squared. So in fact you can write gt as d square, so it will also have d square, so it will also have d square regularity, which is, yeah, very good, because now, so you can imagine, so you can have exponentially. So let's say t was some 10, so let's say d was some, let's say 4. Then you'd see that you could create graphs of increasing size, let's say 4 power. So you would create graphs with huge number of vertices, even thousands and even millions, or however large you like, but it would only be 16 regular. And the best thing about those would be, which is my claim 3, is that lambda 2 of g power gt is less than equal to 1 by 2, sorry. So again, yeah, it's not as good as 1 by 8, but it's still quite nice. So yeah, so the proof of this would be, like, you can give an inductive proof for this as well. So lambda 2 of g1, we saw that when you do square, the lambda thing, it decreases, so it becomes, so this thing will be equal to lambda 2 of h whole square, which is less than equal to 1 by 64, because of the bound we had assumed on lambda on h. And when you do lambda 2 of g2, we saw that this was less than equal to, yeah, I think I wrote an equal to over here, which should, oh no, okay. So yeah, we know that lambda 2 of the zigzag product is less than equal to this thing. So we see that this is less than equal to lambda 2 of g1 squared plus 2 times lambda 2 of g2, where g2 means h, sorry. So this is 1 by 64 square plus 2 into 1 by 8. So there is like 1 by 4 and some very small thing, 64 squared. So if you can keep repeating this, and you'll see that it remains less than equal to half in the infinite sum as well. So that's how this works. So we have constructed an explicit family, and our final construction would be similar to this, but not exactly. So yeah, we have constructed expander graphs, and we have seen very good properties of expander graphs, and we have also seen a method to construct expander graphs with constant degree, because the degree of all of these are d square, but the size keeps increasing. So from this we can finally come back to our problem UST con, which was undirected ST connectivity. So earlier we showed a deterministic algorithm which worked in LogSpace and was able to deterministically find out whether S and T were connected by enumerating all the paths of length log n. And now what we want to show is that UST connectivity is in L. To do that, what we need is a proper algorithm which does this work. So the algorithm is as follows. So given an input graph GST, so this is a brief, like an overview of the algorithm. So what you do is you transform it into some, let's say, G naught, S naught, T naught, in a way that we will describe later, such that this thing is an expander graph, and also that S naught and T naught are connected if and only if S and T are connected. Then the second step would be to check connectivity of S naught and T naught using the algorithm we discussed earlier. So I'll just write it like this, and this can be done in LogSpace. This can be done in LogSpace because of the fact that G naught, S naught, T naught is so G naught is like an expander graph, so we know that this can be done in, for this thing it can be done in logarithmic space, sorry. And so yeah, that's it, I guess. So this construction is again a bit more complicated. I mean, it's not as easy as the earlier one that we had done. So what you do to do this construction is, so let's call it step 1. So what you have is, you assume that H is a deregular graph with d power 4 vertices, and so yeah, let's say lambda 2 of H is like less than equal to 1/4. So yeah, for some constant d, you have some constant graph H which is like deregular with d power 4 vertices and with this property. So what you do is, for k in 1 to L, you keep applying this. So you do gk is equal to gk minus 1 square zigzag product with H. Then yeah, this is how you will construct the new graph. And yeah, finally you will be left with GL, and here L is order log n. Yeah, finally you will be left with GL, and our claim is that GL works. So basically GL is a graph which is an expander graph, and it has all the good properties that we want. Again, the easy properties to see would be that the easy property to see in GL would be that, first of all, the vertices in GL would be sorry. So yeah, the vertices in GL would be quite large, but it would be only be, so we earlier saw that it was exponential, sort of exponential in L, and if it's exponential in L, so it would be polynomial because of the fact that we are doing because L is order log n, so it has polynomial number of vertices, so that's fine. The second thing would be that, so note that we are always doing the zigzag product with H, and H is only D regular, so GL is D square regular, which is very nice because this is constant, so that's very good. And again, the next thing would be about the convergence rate of the, I mean the spectral expansion. Yeah, so this thing also is less than equal to, I'm not sure what the exact bound here is, but we can show that it's less than 1, and in fact less than a half, I think. I'm not sure about that, but we can see that it will be small, again using the similar arguments that we had earlier. So yeah, the idea is that, basic idea is that it's an expander graph. The idea is that GL is an expander graph, and since it's an expander graph, we can check its logarithmicness. We can check the connectivity in it easily in LogSpace. Now the only thing that are left is to check that this transform can be done in LogSpace. That is again a bit, the analysis of it gets a bit complicated, so it involves a very few clever tricks and all that stuff, so we'll again be skipping because I'm running out of time. But yeah, we can actually show that this can be done in LogSpace. That was in fact the main thing, I think. So if you can show that you can reduce GST to GLS, it should actually be GLSLTL, then it works. Except yeah, one thing also you'll have to again figure out yourself, that if S if S and T are connected, so yeah, if S and T are connected in this thing, then it would also be connected in the new graph. That's the one of the main things. So yeah, the way that we have constructed the graph, you can note that, so how we define SK and LT remains to be seen. So how we define SK, so SK and TK are, let's see, so yeah, SK and TK can be any two vertices, or any two vertices in the clouds which we described in the sense earlier, are any two vertices in the clouds of SK minus 1 and TK minus 1. Sorry. So yeah, that's the thing. So SK and TK are any two vertices in the clouds of SK minus 1 and TK minus 1. So all you need to know is, so all you need to show is that if SK and TK are connected, then this implies that SK minus 1 and TK minus 1 are also connected. If you actually look at the definition of zigzag graph, this becomes zigzag product, this becomes easy and actually fairly trivial, but yeah, it seems a bit opaque when you view it like this. But the general idea is that if SK and TK are connected, then SK minus 1 and TK minus 1 are also connected. So if we can find whether SL and TL are connected, we can actually, so yeah, we can actually infer whether or not S and T are connected. So yeah, this was the entire algorithm. So yeah, that's how it works. So you reduce GST, so you reduce G to a graph which has, let's say, logarithmic diameter, and then you check out all paths of length log n starting from S, and then if you find your corresponding SK, SL, if you find corresponding TL, then you know that S and T are connected, and otherwise you know that they are not. And yeah, this can be done in logarithmic space, because this could be done in logarithmic space. And the next step, as we saw earlier, checking connectivity, this could also be done in log space. So yeah, this actually shows that the undirected ST connectivity is in L. Yeah, that's the thing. So I think that should be enough. So yeah, I think that should be enough. Thank you.